Dr. Pietro Paparella. He's an associate professor in the Division of Engineering and Math in the School of STEM. And his research interests lie in non-negative matrix theory, and he's going to tell us all about that. This was his work on it as a result of SRCP funding. Okay, Dr. Paparella, take it away.
Okay, thank you for the introduction. Okay, so I'm going to talk today about polynomials that preserve non-negative matrices, and it's non-negative matrices of a fixed order. This is joint work with Benjamin Clark, who was a student at UW-Bothell, and he started out as a computer science major, and he took an abstract algebra course with me. And after that, he decided that computer science wasn't for him, and he wanted to go into mathematics. And he completed a second degree in mathematics. He was working at, he even landed a job at Google, and decided to leave that career and go to graduate school. And so he's currently a graduate student at Washington State University. I was supported, as Anne said, by an SRCP seed grant, and Ben was supported by a Founders Fellow Award. He was actually awarded or given the grant in like 2018. It just took me a really long time to get back to the project and complete the manuscripts, and that's what the seed grant allowed me to do. Unfortunately, just a bit of warning, there's no way for me to, like, this is going to be very technical mathematics, and there's just no way around it. So just a brief overview. I'll talk about the research products that were produced. And then I'll give some background and the motivation for the work. So we'll talk about matrices, eigenvalues, and eigenvectors, the Perron-Frobenius theorem, the non-negative inverse eigenvalue problem, and then the actual research problem. And then the results are just divided up into some basic results and main results. And there's really just one concluding remark, and it's a problem that we posed in one of the papers. So one of the papers that we produced appeared in linear algebra and its applications. And this is an Elsevier journal, and it's actually the top journal for matrix theory and linear algebra. And it's in general a very, very good journal. The other piece, or the other research product, appeared in a undergraduate journal called Mathematics Exchange, which is hosted by Ball State University. Informally, and this is, I have some of my advanced linear algebra students here, but informally, a matrix is a rectangular array of numbers. But for the purpose of, or for many purposes, the entries are either real or they come from the set of complex numbers. And this is because the complex numbers represent the algebraic completion of the reals, and we basically need to work with complex numbers a lot of the times. So as an example, and matrices are typically denoted with capital letters. This would be a 2x3 matrix. So it has 2 rows and 3 columns. And as far as notation, so we use capital letters for the matrix, and then we lowercase the letter with double subscripts for the entry in the ith row and the jth column. So for that particular example, A12 would be B, because B occurs in the first row and second column. And with matrices, you really want them to be square, or it's the theory of, or the algebra of matrices is richer when the matrices have the same number of rows and columns. This allows for invertibility and eigenvalues, which we will talk about. And then just a bit of notation. The set of n by n matrices with entries from F is denoted by this M sub nF. And then F there will stand for either R or C. There's a particular type of non-negative matrix that's, or excuse me, particular type of real matrix that's important. And it has obvious applications in the sciences, because when you're dealing with measurements, typically measurements are non-negative. And so we actually use the greater than or equal to symbol. And what this means with a matrix is that all the entries are non-negative. So there's no complex entries, obviously, and then all the entries are real, but they're non-negative. So for instance, this 3 by 3 matrix is non-negative. So there's no negative entries to speak of. If we take a complex number lambda, we call that an eigenvalue of A if there is a non-zero vector V such that AV is equal to lambda V. Informally, what's happening here is that the effect of this matrix on this vector is a scaling. Now, this seems like might be just a curiosity, but it turns out that in a sense, the eigenvalues of a matrix, it's kind of like the DNA. The eigenvalues tell you a lot about the matrix. This vector here is called an eigenvector of A associated with lambda. They are not unique because you can scale an eigenvector by any non-zero scalar and produce another one. The traditional notation for the list of eigenvalues is sigma of A. And a non-trivial fact is that an n by n matrix has n eigenvalues, including repetitions. This is because the eigenvalues come from what's called the characteristic polynomial, and polynomials can have at most n zeros, counting multiplicities. So eigenvalues are connected with roots of polynomials. An important quantity for a complex matrix is the spectral radius. And so for the complex numbers, there's a way to measure them in the plane, and it's essentially the distance from 0 to that complex number. And so the spectral radius represents, so if it's the smallest circle that contains all the eigenvalues of a matrix. And there's a colossally important theorem in matrix theory, which is known as the Perron-Frobenius theorem. And what it says is, what it says is that if you have a non-negative matrix, the spectral radius is an eigenvalue. And in addition, you can select an eigenvector associated with that eigenvalue to be non-negative. This was first proved by Oscar Perron in 1907. He was working on, of all things, continued fractions, so something very, very abstract. And then Frobenius extended the work to irreducible matrices. You know, just going back to this, you might say, okay, who cares, right? Well, it turns out that the Perron-Frobenius theorem has applications in probability theory, dynamical systems, economics, demography, the study of social networks. And then I highlighted this one because, so a little bit of history. My academic grandfather was Hans Schneider. He was a professor at Wisconsin. And this tends to happen in mathematics, where someone proves like a big result and then it goes dormant because just, you know, people just forgot about it. Maybe not so much nowadays with the internet and how things are, you know, you can find things so much easier, but, you know, these theorems were proved in, you know, 1912, and then, you know, there was 2 world wars and all kinds of mayhem. And so the Perron-Frobenius theorem had to be rediscovered, and one of its champions was Hans Schneider. And because he brought it back into, he kind of, told people to look at this, that there was more work that got into it. And then eventually the founders of Google, they used the Perron-Frobenius theorem for the original algorithms for ranking web pages. So the eigenvector is really, really important. And you could say that the Perron-Frobenius theorem is the most lucrative theorem in all of mathematics, because it created, it's what underpins Google, at least originally, right? So with the search engine optimization and ranking of web pages. And so you can use it to like, even like say rank football teams, or if you want to rank just about anything. So the problem, or the main problem that I've worked on in my career is what's called an inverse problem. And in particular, it's the non-negative inverse eigenvalue problem. And the idea here is, if I'm given a list of complex numbers, is it the spectrum? So is it a spectrum of a non-negative matrix? So this problem for like a generic matrix, like not asking whether the matrix, or not requiring that the matrix is non-negative, it's a trivial problem, because you can just put a diagonal matrix with these numbers on the main diagonal. But requiring like a certain structure on the matrix makes the problem very, very difficult. So if lambda is a list and A is a non-negative matrix with spectrum lambda, then lambda is called realizable, and A is called a realizing matrix for lambda. And there's some there's some strict necessary conditions. So the eigenvalue of maximum modulus has to belong to the list. And now here's where we're going to start to get into some really technical details. So this SK lambda is called the kth moment, and these quantities have to be non-negative. These two conditions are fairly straightforward. The first non-trivial conditions, which relate the moments to each other, were first established by, so they were established independently by Johnson, who is a frequent collaborator of mine, in 1981, and by Loewy in London in 1979. And the problem that Ben and I tackled comes from this 1979 paper. So as you may or may not recall, a polynomial is basically a function of, it's a linear combination of the power functions from t0 all the way up to tm. And of course, the coefficients there are given, and they're either real numbers or they're complex numbers. And if am is not equal to 0, then m is called the degree of p, and we denote that as deg p. And if we have a given list of numbers, so a given list lambda, we will define p of lambda to be each of these points that we're going to evaluate p at each of these values. So one thing, and this was noted by Loewy in London, is that if p is a polynomial, I got a little bit ahead of myself here. Let me just go back here for a second. I talk about this in a subsequent slide, but with matrices, there's a natural addition, and there's an exponentiation and a multiplication defined. So you can take a polynomial and evaluate a matrix. So you can replace that letter T there with A, and we'll see that in a subsequent slide. And so if if we have a polynomial that preserves the non-negativity of a matrix, so the idea here is if you drop a matrix into this polynomial and the output is a matrix that's also non-negative, then this new list has to satisfy those previous conditions that we listed. And so this was the remark that I made just a second ago, is that we can replace the scalar T with a matrix A. And so Loewy and London in that 1979 paper, they wondered whether 1 and 2 are sufficient for the NEAP. That would be a complete solution to the problem. I suspect that it's not true, but we're far away from proving this. So they asked for a characterization of this set Pn. And so these are all polynomials that preserve non-negative matrices of a fixed order. Interestingly, no one looked at this problem like at all until maybe like there was a paper that came out in 2006 that they looked at this problem in a different way, but just examining this set, like no one looked at it. And this problem is a generalization of a classical problem in mathematics. So the case actually n equals 1 is solved. We know that one for sure, but in terms of the coefficients, it's not solved. And so that's, for me, it was important to find for this problem is to find necessary and sufficient conditions in terms of the coefficients of the polynomials, and that's what Ben and I looked at. And as I mentioned, there hasn't been much work in this area. So one thing that is fairly obvious is that Pn sub 1 is contained in Pn, and they always say that there's a general guideline that you should always have a proof in a math talk. So my students, I've got several students here in attendance, they'll appreciate this. So the idea here is if you take an n by n matrix and a non-negative number x, you can form a block diagonal matrix, which is non-negative. And so if P preserves, if P is a polynomial that preserves all n plus 1 by n plus 1 non-negative matrices, it has to preserve this one. And since A is arbitrary, it follows that P has to belong to Pn. So much of this might be like obviously very foreign, but like, for people that work in the field, it's a very elementary, it's a pretty obvious result. Something that was stated that was, a lot of people said it was, this is just obvious. I didn't think it was. And I managed to find a proof from another paper I had written for my PhD thesis, is that if P belongs to P1, so all this, and belonging to P1 just means that you preserve non-negative. So P maps non-negative reals to non-negative reals, is that the coefficients must be real. And so then we get a corollary that if P belongs to Pn, then its coefficients must be real. And that's because Pn plus 1 belongs to Pn. And so if you belong to Pn, basically you belong to P1. So there's a construction for functions called the even and odd part of a function. And for polynomials, the even part actually corresponds to the even indices, and that's actually where the term comes from. And the odd part corresponds to the odd indices of the polynomial. And one of the things that Ben and I did is we generalized this construction for what we call the R mod n part of a polynomial. So this is all the congruences modulo a specific positive integer. It's hard to explain without, so the even and odd part corresponds to when n is equal to 2. So if you go back to this here, that k congruent to 0 mod 2, when you take a number and divide it by 2, there's 2 possible remainders, 0 and 1. And so the indices that we're interested in are even and odd. Well, if you divide an integer by 3, the possible remainders are 0, 1, and 2. And so you can take a polynomial and compute three things to it, but we don't call it even and odd anymore because there's a 0, 1, 2. So that's why we called it the R mod n part. And we proved that a polynomial is basically the sum of these parts. That's what that condition there says. In another paper that included an undergraduate researcher, they came up with a formulation of this R mod n part. And this is for general, like, complex functions f. And what we proved is for polynomials, our construction matches theirs. So it's the same idea, it's just a different form. There's something that in mathematics you want to do. You know, someone might find our construction more useful instead of like say someone needs to use this construction by and I'm not sure how to pronounce their names, but Balik or Barlach and Andres. Like if they find this hard to work with, they can use our construction, at least for polynomials. There's a specific type of matrix called a Jordan block, and it's an upper triangular matrix with T along the main diagonal and then a bunch of ones on the super diagonal. And these are really the building blocks for matrices, but they also represent things that are not very well behaved. But when you evaluate a Jordan block with a polynomial, it has a very nice explicit structure. And because of this form, and the idea here is that along the super diagonals, you're basically just computing derivatives of the polynomial. And so we immediately get that if P belongs to Pn, then all of its derivatives belong to P1. So all of its derivatives have to preserve the non-negativity of non-negative real numbers. And so one of the things that we were able to prove, if P belongs to Pn and M exceeds is greater than or equal to n minus 1, then the first n terms, so that's the first n of the coefficients, have to be non-negative. And if m is less than n minus 1, then all of its coefficients have to be non-negative. This is something that was known, but we proved this in some different ways. And this is because the kth coefficient is the kth derivative evaluated at 0 divided by k factorial. K factorial is a non-negative quantity, so that quantity must be non-negative. There's also an algebraic and geometric structure to this Pn. And so if you take one of these polynomials and scale it, you get another one. If you add two polynomials, you get another one. So this is what's called a closure property, but also the fact that this set is closed with respect to non-negative linear combinations tells us that we have a cone, so a mathematical cone. And this actually follows for some non-trivial facts for evaluating matrices, or evaluating generalizing functions where the inputs are matrices. And this is actually something that I did for my PhD. I know a lot about because I had to do this for my dissertation. And so this is something that I just mentioned, is that Pn is actually a cone. Another theorem that we proved is that those R mod n parts also have to belong to P1. This was not something that was known before Ben and I worked on the problem. And this is what I was talking about or referencing earlier, is that it's nice to have some inequalities in terms of the coefficients of the polynomials, and not some like esoteric condition that you can't really test very easily. So let me give an example of this result that actually rules out a polynomial. So here's a degree 3 polynomial in X, and if I sum the coefficients over the even indices, that's what that sigma says with the notation underneath. So if you look at the powers tell you the coefficients because it's 3, 2, 1, 0. So the even coefficients are -1 and 2. That's non-negative, right? And then if I sum over the odd coefficients, so that's 1 and -2, that's negative. Because that sum is negative, we can conclude that P does not belong to P2. So it's a necessary condition. It's not sufficient, but it's necessary that those inequalities have to behave this way. Because of that inclusion, we have to have some similar, we can basically vary that R quantity from 0 to hat n minus 1, and then hat n goes from 1 all the way up to n as well. Something else that was actually a really good result for us is that if the degree of P is greater than m, excuse me, then the last n terms also have to be non-negative. And so we get a corollary is that if the degree of a polynomial is less than 2n, then P belongs to Pn if and only if all the coefficients are non-negative. This was not known before at all. Like, it's really clear that a polynomial with non-negative coefficients obviously belongs to Pn, but no one knew like how big the degree could be. And so this gives a precise upper bound that if the degree is strictly less than 2n, then all of the coefficients have to be non-negative. Something else that we worked on, so I mentioned earlier that there's a containment result that's very obvious, and we tried to prove that this containment was strict, meaning that there are polynomials in P1 that are not in P2. We were able to prove that in the paper in Mathematics Exchange. Actually, sorry, that's the LAA paper. CP2 is the paper for Mathematics Exchange. We proved that P3 is contained in P2 by providing some examples. And then we conjectured that P of n plus 1 is strictly contained in Pn. And the reason why I didn't include this in my concluding remarks is because our old friend Rafi Levy is a really nice guy. He's at the Technion in Israel. He saw my work. You know, this is the problem that he laid down before I was born, and all of a sudden he got back to work on it, and he posted a preprint. I'm assuming it's in review because I haven't seen it published anywhere, but he's got a proof of that conjecture. So already it's triggered an interest in, you know, people are working on the problem again. I've gotten some good feedback that, you know, there's some serious people in analysis taking a look at this problem. And then one of the things that we also that we also want to know are the extreme directions of the cone, because basically a cone, if you have a what's called a polyhedral cone, that the extreme directions, all you need to know to characterize the cone are the extreme directions. And so we want to know what functions lie on the boundary of the cone. So that's it. And thank you to the Office of Sponsored Research for the support.
Great. Thank you. That was fascinating. I'd like to invite your students to react to what you've just shared with us. Thoughts, questions?
So how did you choose this topic of research, like specifically this problem? I know that you're very into matrix and linear algebra, but this specific problem, how did it come up in your mind?
I was rereading, so I'm really familiar with that paper that Loewy and London published. I had embarrassingly, there was a part of the paper that's always referenced by people that are working on the NEAP, the non-negative inverse eigenvalue problem. I just never bothered to finish the rest of the paper. And then at the end of the paper, they were like, hey, these polynomials, no one's worked on them, and it would be nice to try to classify them. And so, for some reason, no one looked at this problem for 43 years. Well, I guess 40 years, because we published that paper appeared last year. Usually you just, you read a paper, and either, the authors will make something explicit, or, you just look at something and say, oh, I think I can do a little bit more than what they did. And that's typically what happens.
So how do you find your students that end up becoming researchers with you?
If I have grant money, I will actually put a formal job posting. But typically I just recruit, I recruit students from my courses. I just let them know if they want to discuss undergraduate research. That they come see me. Sometimes as far as the recruiting, I might email a student and say, if there's certain students that are doing exceptionally well, ask them if they want to do research. This last summer, we had a math REU at UW-Bothell. Unfortunately, we're not going to run it this summer because of space. But that's another avenue for undergraduate research.
I have one more that I'm dying to ask. Oh, Sarah, go ahead.
Did you use computers or anything to help you figure out that theorem, or did you work just chalkboard and work through, did you manually just work through it? I'm just kind of curious what your process was, or you and your students' process.
So as far as my process is concerned, I will use MATLAB or Mathematica to gather data about something, but ultimately math is an art that requires a proof of, if you want to establish something, evidence is not enough, scientific evidence. So you have to make an argument as to why something is true, and it's always true. There are some experimental results are of value. They just kind of lead the way. But for this project, there really wasn't a lot of software we could lean on because of visualizations, because the dimensionality is too high.
Right.
So as soon as you get into a 4th degree or even a 3rd degree polynomial, degree 3 polynomials can be viewed as vectors in 4 dimensions. And so that's a problem.
Right. Great. So you just hashed it out.
Yep.
Way to go.
Well, you addressed the question I had in your comments just now. So I was wondering about the process too, because I mean, in engineering school, I remember my first calculator that could solve a matrix. And it was like, it was groundbreaking. Of course, that shows you how old I am. But yeah, just hashing it out. I'm fascinated by your process. Thank you very much, Dr. Paparella, for your presentation and your research.